Okay, in this video, we're looking at vector calculus. So vector calculus, similarly to actual calculus, you can differentiate and integrate vectors just like you can functions of x and y. There is a first principles derivative that we will look at in class. I don't want to spend too much time in the video covering it. But basically, if you have a position vector r of t, and you want to find the velocity vector of that, then it's just going to be x dash t I plus y dash t j. So deriving the x and y components to find the derivative of r with respect to time, which is the velocity vector t. So speed is just going to be the x component squared plus the y component squared. The acceleration vector is going to be the second derivative. So x double dash t I plus y double dash t j. And like I said, we'll go into a bit more detail of why that just works. It's very convenient that it works. It is constructed using vector addition, and then taking a sort of delta, a change in position along the curve as that goes to zero. So using a limit definition, just like we did when looking at calculus for functions. So momentum is the quantity of motion that an object has. It's dependent on both the mass and speed of the object. So momentum is given by P is equal to m times the derivative of r, which is velocity. So with vectors, textbook notation for the derivative of a vector is to put a dot above it. So this would be r dot t, which is the same as m v of t with the vector symbol beneath it. So that's momentum there, given by p. So we're given the following particle with a position vector of r, and we're asked to determine the velocity of that vector. So t cubed plus 6 sine 3t, and then plus 12e to the t on 2k. So this is a three-dimensional position vector. Its three-dimensional velocity vector is going to be r dot t, which is equal to d dt of t cubed I plus d dt of 6 sine 3t j plus d dt of 12e to the negative t on 2 k. So differentiating all three of those, we get 3t squared I. We then get 18 cosine 3tj. And then lastly, of course, we would get 6e to the negative t on 2. So 6 minus 6e to the negative t on 2k. So for the acceleration vector, we then just derive it again. So r double dot of t is going to be 6ti minus 54. So it'll go from positive cosine to negative sine of 3tj. And then we're going to have plus 3e to the negative t on 2k. All right, so if we wanted to find the gradient of a curve, can be found by either using implicit or explicit differentiation. So if we were looking at a curve of f of x of y is equal to a constant, then dy dx is going to equal dy dt times dt dx, which is the same thing as the derivative of y over the derivative of x, right? Because if we're multiplying, that's the same as dividing by the reciprocal. So a particle moving with position vector r there for 0 to pi seconds t. Determine the coordinates where the tangent of the curve is parallel to the x-axis. So first of all, let's split this into x of t and y of t. So x of t is going to be 3 take 2 cosine 2t. Y of t is going to be 2 plus 3 sine of 2t. We're asking where is it parallel to the x-axis. So the tangent of the curve is going to come when the gradient is 0. So when the gradient of this curve is equal to 0, it's going to be parallel to the x-axis. So to find the derivative, we want to find dy dx, which, as we looked at earlier, is going to be y dash on x dash. So y dash on x dash, y dash is 3 cosine of 2t, and x dash is given by 4 sine of 2t. So that's just deriving these two equations up here with respect to t. Let's actually include the t here so that we can visualize that. So simplifying this out, we get that... we did have 6 on 4, but I've already simplified that. So simplifying that out, we get not 3 on 4, but 3 on 2 rather. Sine of 2t. And we're asking, when is this equal to 0? So dy dx equals to 0. That's going to give us a flat gradient. So the tangent to the curve with a flat gradient is going to be parallel to the y-axis. That's what we're looking for up here. So 0, we don't care about the denominator. We don't care about this 3. This cos of 2t is what's determining whether it is equal to 0. So this is just asking, when is 0 equal to cos of 2t? But we also need that sine of 2t is not equal to 0, because at that point the derivative is undefined. So our values of that is going to be 2t is equal to the inverse cosine of 0, which is going to be pi on 2 and 3 pi on 2 in our domain. So t is going to equal pi on 4 and 3 pi on 4. So when t equals pi on 4, we get that, substituting back in, we get x is equal to 3 take 0, which is just 3, and we get y equals 2 plus 3 times 1, which is 5. So our coordinate's going to be 3, 5, where the gradient is 0. And then at t equals 3 pi on 4, we're going to get that x is equal to 3 and y is equal to -1. So that just comes from substituting this value of t back into that original two equations for x and y. Okay, so those are our 2 points at which the tangent of the curve is parallel to the x-axis. Part B, we are looking at the Cartesian equation of the path, sketching the path, and then stating the domain and the range. So we have the x and y. We're going to rearrange to make cosine and sine the subject, and then add these two together using the trig identity. So cos of 2t is equal to x take 3 on 2, and it's actually on -2. And then sine of 2t is going to be y take 2 on +3. And so adding the squares of these, we're going to get 1 is equal to negative x take 3 on -2. When we square that, that negatives going to become a positive. So this will be x take 3 squared over 4 plus y take 2 squared over 9. So that's the equation. This is an ellipse. So we have center of 3, 2. We have a domain of 3 plus or minus 2, which is our b value, and we have a range of 2 plus or minus 3, which comes from our, that comes from our b value, and then plus or minus 2 comes from our a value. So our domain is 1 to 5, and our range is -1 to 5. And this is centered at the point 3, 2. I'm going to leave it as an exercise for you to sketch that. And part C, we've got the maximum and minimum values of speed. So the maximum and minimum values of speed is going to be based off the magnitude of r dot of t. So the magnitude of r dot of t is going to be equal to x prime squared, so x, the derivative of x squared plus the derivative of y squared, which in this case is going to give us the square root of 16 sine squared of 2t plus 36 cos squared of 2t. The maximum, well, first of all, we can use the Pythag identity to replace sine squared with 1 minus cos squared. That's going to give us square root of 16, just 16, minus 16 cosine squared 2t So grouping our like terms there, we get that that is equal to 2 root 4, so taking out a factor of 4, or square root 4, plus 5 cosine squared 2t. So the reason why we've represented it in this form is because we can see that the maximum value is going to be determined by cos squared of 2t. So the maximum value of that is 1, and the minimum value of that component is 0. So this is going to have minimum value of 2 root 4 plus 0, which is 2 times 2, which is 4. And then it's going to have a max value of 2 root 4 plus 5 times 1, which is going to be root 9, which is 3. So it's going to be a maximum speed of 6. So minimum value comes from 5 cos squared 2t being 0, and then maximum value 5 cos squared 2t being 5. So let's take a look at the next example. This is an application of what we've just looked at. So the position vector of a golf ball at t seconds is given by that function there, where the distance is in meters. Determine when and where the golf ball hits the ground. So the golf ball is going to hit the ground when the y component is equal to 0. So y of t is equal to 0. Therefore, 20t take 4.9t squared is equal to 0. We can solve that out to see that t equals 0 or t equals 4.08 seconds. So at t equals 0 and t equals 4.08 seconds, the ball is at ground level. But it's saying when the ball hits the ground, we're assuming at t equals 0, it's not hitting the ground, it's starting at the ground. So our answer is that second value there. Part B, determine the initial speed and angle of projection. So the initial speed, for part A, we found when it happened, but we didn't find where it happened. So we know that y equals 0, but we need to know what the corresponding x value is. So we substitute 4.08 back in there. We get 15 times 4.08, which is going to be 61.2 meters from the initial point. Okay, part B, determine the initial speed and angle of projection. So to determine the initial speed, we need to find r dot 0. So that's the speed at t equals 0. So r dot is going to be 15I plus 20 take 9.8 times t j. So substituting in 0 for that, we get 15I plus 20j. The magnitude of 15 plus 20 is going to give us 25 meters per second. So it's just a 3, 4, 5 triangle, but each side's been multiplied by 5. The angle is going to come from the inverse tan of the y component over the x component. So if you imagine this is our angle of impact, we know that it's got a speed vector coming up of 20j and a speed vector coming out of 15I. So the angle is going to be tan inverse of opposite over adjacent, tan inverse of 20 over 15, which gives us 53.13 degrees. That's actually the angle of a 3, 4, 5 triangle, so it's good to see that there. So it's got an initial speed of 25 meters per second and an angle of 53.13 degrees. Part C is asking us to calculate the maximum height reached. So the maximum height is going to be when y dash t is equal to 0. So that's when the vertical speed is starting to slow down. So that's going to be equal to, we solved this down here, it's 20 take 9.8 t. Where do we think that 9.8 is coming from? Well, it's probably gravity, right? Because it's a ball going up into the air, and we have the fact that gravity on Earth is 9.8 meters per second squared. So if we've got a velocity, it's being multiplied by that acceleration to each second of time. So this is going to give a value of t is equal to 2.04. So the maximum height reached is going to be y of 2.04, which is equal to, if you substitute it in and check, 20.41 meters high. Part D, we want to show that the golf ball travels in a parabolic path. So to do that, we want to write out our parametric equations. So x equals 15t, y equals 20t minus 4.9t squared. So if we were to substitute this t in for there, we'd get that y is equal to 20 times x on 15. So that's come from rearranging this to make t the subject, minus 20 times x on 15 squared, which gives us textbook solution has factorized it, so it's going to be negative x on 2,250, 49 take 3,000. I see what I've done wrong. This 20 should be 4.9. So they've done it in a way so that the coefficient of x is an integer. But we can see this is a parabolic equation. We've got a leading term of x squared when that's expanded. It's just of the form here ax x take b. So a is less than 0, therefore the golf ball travels in a parabolic path. That's all we're going to cover for this video. The next video will be on integration of vectors. I'm going to leave that for a separate video.